Okay, here's a little bit of an off-the-cuff little lecture about various kinds of infinity. Probably, if you've seen lectures on different kinds of infinity, this probably is not the one you've seen. And I've given some of those. I have some top videos on it. So here's what it was motivated by. Teaching a class, and I was just asking the question, just a conversation starter, these kinds of questions. Is 1 over 0 equal to infinity? Is 1 over infinity equal to 0? Okay. Okay. So, um, and really depends on what you mean by this symbol infinity. Okay. And in most situations, no. That's super uncareful. But I want to talk about how it's actually an interesting question. Okay. So, um, uses. It's really uses of the notion or generalizations of the notion of infinity. Okay. So the first place you usually first see it in any sort of official mathematical uh, setting is infinity as like a limit direction, a trend indicator. Absolutely not a quantity that you do algebra with or plug into formulas and things like that. So this is where you'd have like the limit as x goes to infinity of some function equals some, let's say, finite number L. Well, that says you have a horizontal asymptote. It's on the right. It says that if you graph this function, as you go out to the right, you approach this height L. And you might wiggle, okay, but you get closer and closer, okay? Or to be a little more precise, but not to bring out the epsilons and deltas, it says that you can make the values f of x as close to L as desired within some tiny preassigned error tolerance, let's say, by making, well, by making x near infinity, sort of, but you can just totally erase the infinity by just saying by making x very large. So x goes to infinity is just a shorthand, purely a shorthand. You could think of it as purely a shorthand, fewer symbols right, then x is getting very large and positive. Okay. So this is a perfectly good use of infinity. It's a nice shorthand, but we usually tell calc students to be very careful not to think of infinity as a quantity or as anything you can actually manipulate. So similarly, we could look at like a vertical asymptote. Same idea. We could say the limit as x goes to like some finite number a of f of x equals, let's say minus infinity, just to bring minus infinity in. So that would be a vertical asymptote at x equals a. And it's saying like this, whenever you get close to a, well, actually, let me be a little more specific. Let's say a from the left, because I don't want to commit myself to having a two-sided limit. Okay. So this is a shorthand for saying that as x gets very, very close to a, the values of x become arbitrarily large and negative. Or to say it slightly better, given any huge, large negative number, let's break the scale here and say this is like, minus 10 to the 10 to the 10 to the 100, I can find some number x close to a, so that when I get down to that number, I will be that far down, and I can get even further. Okay. So, not to make this into a lecture on limits, but this is a very good and very common use of infinity, but it's really just as a placeholder for a more long-winded thing about limits or epsilons and deltas and things like that. Okay. Again, it's really important that in this use, it's not something to plug into functions and try to get a values out, or do algebra with. You wouldn't even try to do like 0 times infinity or 1 times infinity or infinity minus infinity. You often have things like this in quotation marks as saying, hey, needs more work, and there's a certain technique like L'Hopital's rule or something that might actually address it. But you shouldn't think of that as, oh, that's equal to 1 because they cancel. Okay, it's super dangerous, and those notations are very dangerous for that reason. Okay, so that's That's one use of infinity. And if you don't go past like a first year calculus class, that's probably all you're ever going to see. And the punchline should be don't think of infinity as a quantity ever. But there's other uses. So the second use is what's called the extended real numbers, usually denoted as a closed interval. You usually, when you're being careful about denoting the real line with interval notation, you're supposed to do it as open interval minus infinity to infinity, exactly because this is just supposed to be an indication of don't stop and don't stop to the left, but don't think of it as there is actually a place where you stop at infinity. So if you make those closed brackets, it's actually saying, oh, there is really actually something at the end called infinity. So this already tells you, hey, we got a new perspective that we're thinking of infinity and minus infinity is actually quantities. Okay, so in this world, infinity and minus infinity can sometimes, in special cases, be the values of a function. They can be the outputs. They're not usually the inputs in this world, but they can be. But they're more often seen as values, outputs of some function. Okay, and you can do some limited algebra with them, and I'll come back to that and give you some warnings at the end of this part. Okay, so here's the case, the most common case where those come up, and that's in the study of a little bit more advanced theory of integration, which usually goes by the name of measure theory or real analysis, let's say. Okay, so actually, yeah, I don't need the title thing anymore. Okay, so here's two situations where you would use this. Okay, one. Okay, so let's say we have the quantity I is the integral over some set. I'm just going to write over some set E of a function f of x dx. And the more general notion of measure theory is that you don't always have to be integrating like from A to B, just like on an interval. You could have some sort of more funky set that has a bunch of pieces and maybe has quite a complicated structure. Okay, and we're not going to use real complicated sets, but I'm going to go ahead and think about it slightly more generally. The integral over E of a function. And that just means for whatever parts E has, like maybe it's this bit and this bit and this bit, you just look at the function there and you just look at the total area under the curve. And you or allow yourself some pretty weird functions where that's actually pretty subtle to even know that there's an area at all. Okay, so here's just really two simple cases where that would happen. Suppose where you get like infinity stuff. Suppose there's a constant, just c dx. Okay, well this is going to be suppose this is like height c, and the same set. Well, we're just going to get height c times however long, what the total length of that set is. If it's just a to b, it's just going to be c times the quantity b minus a, because that's a very simple rectangle. In general, it's c times what's called the measure of e. And we use this special word measure because, again, it might be some weird set, but basically you want to think in this context where we're just like on the real line, it's just a flexible measure of length and a total length if it's in different pieces. Okay. So I'm just telling you how to integrate constant functions. Very, very simple. But what if we had two extreme cases? Okay, or an extreme case of this. Extreme case of this is that the set is the entire real line. Or in other words, in more standard notation, the improper integral from minus infinity to infinity. Oh, there's another use of infinity seemingly. It's really the same use as we had before. Maybe I should have broken it out as a different use of infinity from Calc 1. But it's really still a placeholder, and you define it carefully by approaching it and with limits. But maybe you should think of it as a different one. So integral minus infinity of c dx. But what if that's 0? In other words, the integral over the entire real line of just 0 dx. Well, so it was supposed to be the height of the function times the length of the interval. Well, that really seems like we're saying that's 0 times infinity. Because if there's any meaning, any quantity whatsoever we could assign to the length of the entire real line, it's really got to be some sort of infinity. And then the area under the curve with height 0 over that whole thing would be 0 times infinity. Okay, so it's really tempting to actually have a definition for this and to have infinity be an honest to God number. This is one of these extended real gadgets. And to be able to do at least a limited amount of arithmetic with it. In fact, it totally makes sense in this context to say that in fact should be 0. So in this context, I'm not saying it's a general thing. This is what's subtle about this. It's very context dependent. You actually define 0 times infinity to be 0 because it turns out that really the absolute right definition of the integral of this function really should be 0. And you have to actually look really, really carefully at the definitions to make sure that that's not a cheat and that it really is okay to define that. I think a lot of people would be like, hey, let's just not try to define that, but it actually works pretty well. Okay, so one other thing from measure theory, another extreme case of measure theory, is suppose I have this really weird function. It's 0 if x is not equal to 0, and it's infinity if x is equal to 0. So that's a really weird, it's really hard to graph. Here it is, it's always 0 down here, and then it's like, woo, going up to this weird plus infinity value. Okay. Let me make a parenthetical comment. This may sound like, it is not what's called the Dirac delta function. That's part of what's called the theory of distributions. I do have videos about that. No plural. Okay. This is very different. So I'm not talking about that. I'm talking about literally something that has the value 0 everywhere at 0 and infinity at x equals 0. And I'm just asserting that this makes some sense with this extended real thing. Okay. It turns out that there are situations where you actually want to integrate that function over, let's say the reals. Okay. Or let's just say minus 1 to 1 maybe. Okay. Well, now what's going on? Okay. It's basically a rectangle now. The width is 0. And the height is infinity. Okay, and so again, it's 0 times infinity. It turns out, again, it totally makes sense to really say that should have integral 0 as well. Okay, why on earth would you have this? Why isn't this just just complete nonsense? Well, just very briefly, where you get functions like this in measure theory is as limits. Again, infinity really, when you come down to it, always has to be defined with some sort of limit process. And so the kind of thing you often have is you have like a sequence of functions. Why would you get a function with infinite values? What's up with that? Well, a situation where you might have that is you have a sequence of functions like maybe it's like this, and then the next function is like this, and 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 those values spike off in maybe a limited place, maybe not everywhere, they spike off to infinity, okay? And then you might have some limit function that has finite values here, and then just infinity, and then, I can't even see that, like infinity going up here, and then maybe back to finite values. So it turns out in certain circumstances, if you're really careful, it's sometimes okay to have infinite limit values. So the extended reals are kind of cool. They're actually, I think they're one of the least necessary versions of infinity, but I wanted to introduce it because it is one of the first places people often encounter if they're getting into like, sort of advanced undergraduate level math, where you actually start treating infinity as something you can manipulate, and it can be the output of a function, maybe the input of a function, and you have these things like 0 times infinity is 0. Certainly 1 times infinity is infinity, 5 times infinity is infinity. These are all meaningful calculations, but not every calculation is meaningful. Like infinity minus infinity is still not defined. Really important that you can't sort of play them off against each other and get in that way and get a meaningful answer. So in particular, it's not incorporated into an algebraic structure that has nice general rules like, oh, everything's always defined and you're always commutative or associative, that kind of stuff. Okay, so it's a rather funky use of infinity, but it's kind of cool to be able to say, yeah, 0 times infinity, that's 0, and I know why. Okay. So in the next part, what I'll talk about is a more topological version of infinity. Something will meld sort of topology and algebra and geometry all together in a very common use of infinity.